Okay, happy Monday. Today is March the 7th. We're covering class number 16. It is our second day on improper integrals, and we'll introduce something called the comparison test. I warned you that there were parts of this newest project that you are working on which are very math proof oriented. Perhaps the first time you're really going to experience writing mathematical proofs. And today's class, we are going to be writing mathematical proofs, and this will help you on the project. I'm also going to hand out quiz number 4. I'll do that during class today. Again, it is a take-home quiz. You're working on it on your own. Projects you can work together, but the quizzes is an individual effort. So I'll hand that to you later today, and you will hand that back to me at the start of next class. Any questions on the calendar? Quiz is due Wednesday. Project is due Friday, the 11th. And then I'll give you a new project on Friday. Yeah. Other questions? Yes, Chris. You will see today. Okay. All right, so let us get started at the top of page 22. Here we go. All right, today we'll be able to determine whether an improper integral converges by comparing it to another integral whose convergence behavior we know. Remember, if one of these improper integrals is equal to a finite number, then we say the integral converges. But if the improper integral is infinity, then we say the integral diverges. So we're going to figure out convergence or divergence today, but typically trying to figure out what something converges to, like last class we had integrals that converge to 10. We're probably not going to be able to get a numerical answer. We'll just have to be happy knowing that something converges, not necessarily knowing what it converges to. Okay, number 1 is another Mathematica player demonstration. So here it is. This is the graph of 1 over x to the n. I really can't make it any bigger, so I apologize to the folks in the back of the room. But 1 over x to the n is this thing, and at the moment, n is 1.1. And in the activity that you guys tackled last class, you found the value of the integral 1 over x to the 1.1 from 1 to infinity. It was the very first thing in the activity. Yeah? And you found that the answer was 10. You guys remember that? And then on the next page, you did the same integral, 1 over x to the 1.1, but instead you went between 0 and 1, and you found that that integral diverged. And so looking at the graph, we've got the two, we can think about the two of these guys together, the 0 to 1 piece and the 1 to infinity piece. There's the graph. The 0 to 1, the problem is at 0. There's a vertical asymptote, so potentially there's infinite area there in the pink. And then the 1 to infinity, the problem is going forever to the right, and this blue area potentially could be infinite. And so the blue in this case was finite, it was 10, and the pink was infinite. And I'm going to take that power, the n, which is currently 1.1, I'm going to start changing it. So if we just drag this guy to the right, just look at the curve, don't look at all the numbers and stuff. But what happens to the blue area? I'm going to go back, we're here. What's happening to blue? Smaller, and what's happening to pink? Bigger. And so still divergent and still finite, smaller. It was 10 a moment ago, but now it's 2, right? But that means as I go the other direction now, the things are reversed. Right now, blue is getting bigger and pink is getting smaller. Now it's still finite and infinite in that order, but do you guys remember what you discovered for the cutoff? Where did they shift? Was it 1? Now, if you're actually at 1, all right, I'll just type in 1 here. The conclusion was they both diverged. That's what we saw, right? They both turned into an ln and they were both infinite. But as soon as you crossed over 1, I think we did 0.9. Was that one of the ones that we did? And so as we cross over 1, the pink goes from being finite to infinite, and the blue, all of a sudden, which was infinite the whole time, crosses over into the land of finite numbers. And so I really like this visualization, just thinking about the way the areas shift around. And for this particular function, the 1 over x to the n, there's a very clear line, like a line of demarcation, where if you're on the right side of this line, you're finite, and if you're on the wrong side, you are infinite. And that line is at the power of 1. Okay? Yeah, they both diverge at 1. I'm running, blah, blah, blah. Okay, so they both diverge at 1.
Now, is that special for any reason?
I think it's just because they both turn into ln, and ln of 0 is undefined, and ln of infinity is infinity. But any power other than 1, you get to use a power rule. So 1 over x is a very special antiderivative case. Every other case besides that power of 1, it's a power rule. And so it's just its own creature because you can't apply the power rule to 1 over x. All right. Our big conclusion from last class, and I think you guys wrote this up on your papers, is that if you're doing the integral from any positive number up to infinity of 1 over x to the p, that guy converged when p is big, bigger than 1, and diverged otherwise. P is less than or equal to 1. And if you go from 0 to any positive number, the problem here is now at 0. There's no infinity anymore. The convergence and divergence is backwards. So these were the conclusions that you made from the big activity. Okay, let's move on to number 3. It says, suppose that 0 is less than or equal to some function f, which is less than or equal to some function g, for x sufficiently large. We're not going to worry about that. Here's an example. The graphs that I've put up here are 1 over x squared and 1 over x cubed. I'm actually going to cross them off. I think they might distract from the point. So just g and f, and you can see that from 1 onwards, the f function is smaller than the g function. Agree? Okay. And now suppose that you know, this is number 4, that the integral from a, we're going to change this a to a 1 just so it matches the picture here. So the integral from 1 to infinity of g of x, which is this light pink one on the top here, converges. So suppose that you know that this entire area here from the pink down to the x-axis is finite. What can you conclude about the area under the blue? It's also finite because it is definitely smaller than that shaded area that is finite, right? So smaller than something finite, still finite. Great. So that's our conclusion here. We can conclude that the integral from the number to infinity of f of x also converges. So if you are smaller than a convergent integral, then definitely you converge, right? Okay, now the other direction. Suppose that we're looking at the f integral, which is this thicker blue one here. What information would be useful to know about the area under the blue one? Would you like to know that that's finite or infinite? To be able to get a conclusion about the area under the pink. We'd like it to be infinite. If that blue area is infinite, then what can you say about the area under pink? It's also infinite because it's even more, right? And so if you know that the integral of f, the smaller one, diverges, then you can conclude that the integral of g also diverges. Because it's bigger, right? If you're bigger than something infinite, for sure you are also infinite. And so those two statements together in number 4 are what we call the comparison test. And we're going to use it all day today and in the homework. And we're going to make sure we reference it by its name. It is called the comparison test. You are comparing two functions, f and g, right? Two integrals, really. Also note that there are other conclusions that you can draw that are false. Suppose that I tell you that the integral under blue, which is shaded in currently, is finite. What can you conclude about the area under pink? Nothing. You know the area under the pink is bigger than that black shaded area. It could be finite, but it could also be infinite. And then along those same lines, if you know that the area under pink is infinite, what can you say about the area under blue? Nothing. It might be infinite, or maybe it's small enough that it's finite, right? It might not be. So there's nothing to say, right? So there's two cases which are helpful. We've written them here. There's also two cases where it's easy to read too much into the scenario. Next page. So 5 summarizes that. We can show an integral converges if we can find a larger convergent integral, and we can show an integral diverges if we can find a smaller divergent integral. And so in practice, what we'll do is try to figure out a simpler function than the one in question, but that has similar end behavior. And we'll do that today, and then we'll make our comparison. Number 6, I'm going to modify slightly. 6 talks about this integral of 1 over e to the ax, where a is some number. Again, I want to be very concrete here. So I've just made up 2 integrals. Maybe you could copy these down here. Integral from 5 to infinity of 1 over e to the 2x, and then basically the same integral, but 1 over e to the negative 2x. Yeah, I changed the limits, but the fact is it doesn't matter, 5 and 7, like it makes no difference what those numbers are. The issue is going to happen at the infinity if there's going to be an issue. Okay, so let's do the easier one first. This 1 over e to the negative 2x in green. This is really the same as e to the 2x, yeah? And think, I'm not even going to do antiderivatives, but just think about the graph of e to the 2x. Looks an awful lot like the graph of e to the x. And if you want to find the area underneath this graph from 7 to infinity, what is it? It's infinite. Like it's like super infinite, right? I mean, like e to the x by itself goes up to infinity. And so this one right here for sure diverges. And I mean it diverges hard, right? And that's not a mathematically defined thing, but you know, like there's no question. Okay, let's take a look at the other guy. Okay, so then are we willing to make this this case that it doesn't matter? It didn't matter that it was the number -2 per se, but any negative number down here is going to flop upstairs and give you that exponential growth. So any negative a right there, for sure, this thing diverges. So I'm ready to fill that blank in. Diverges if a is less than 0. So if a equals 0, that's a good question. So if a is 0, 1 over e to the 0x, which is 1 over 1. What's the integral of that? X, whoops, x. Well, we don't even need that. Just think about the graph of 1. So converges or diverges if you think about that area. Diverges, right? It's constantly 1 forever. So that one's also infinite. So that means the equals 0 is in this divergent camp. And now let's have a look at blue over there. So this guy is equal to the integral from 5 to infinity. We'll bring that guy upstairs. So now it becomes e to the negative 2x. Antiderivative here does require a u substitution. I'm just going to write the final answer here. You can check it later on, but anybody know? Is that right? Is that right? And that's a derivative. We want an antiderivative. Yeah, it's this over -2. That's right. And then we're going from 5 to infinity. I'm being super lazy here. Putting an infinity up there is no good mathematically. Like notationally speaking, that is no good. What should I have put? A limit and a b, right? You're going to do that for me on the project. Yes, the b is the bracket is the last possible spot to introduce the b. It's okay to have the infinity on the integral itself, but as soon as you leave the integral, it's got to change. But we'll be lazy together here. So this is a 1 over -2 e to the 2x from 5 to infinity, right? Just makes it easier for me to plug in to have a positive exponent. Okay, and so when we plug 5 in, we get some number which is irrelevant, right? The question is what's going on at the infinity. What is going on at the infinity? It goes to 0, right? If you let x get bigger and bigger, then you got 1 over some enormous negative number. So 0 minus some number. So converge or diverge? Converges. And in fact, any positive number down here, and it's going to be this same exact calculation. Right? Wasn't special about 2. It could have been 200. It could have been 0.02. Any positive number, that E is for sure staying downstairs all the way through the calculation. And as soon as there's an E down there, it's going to go to 0 when you send x to infinity. So that's the other blank. Any actual positive value of a, the integral converges. Negative or 0 value of a, it diverges. Okay? Okay. All right. So we now have a large list of integrals that we're going to just say are easy, that we know whether they converge or diverge just by looking at them because we've made all of these big conclusions. So here it is in summary. We're going to call these the useful integrals for comparison. The first two are the ones we talked about earlier today, that you made these conclusions in the group activity. It's about 1 over x to a power, right? So we've got those two. And then the brand new one is this e to the ax business, which we just did up above. So we've got these 3 different things that we're just going to say, hey, anytime we want to compare to one of those 3 kinds, we've got our conclusions. It's all ready made for us, and we're going to reference these facts many times today. Okay, so moving on to page 8, or to number 8 on the next page. So there are 3 problems here. I want to give you guys a little bit more time in the activity and less time watching me. So we're going to skip part A and just do B and C. But A is good practice for you later on if you're looking for even more practice to try after the activity. So the question is, in number 8, determine the convergence or divergence for these integrals. Be sure to justify. So let's jump down here to part B. So we've got this crazy integral 1 to infinity of 4x over x to the 4 plus 4x squared over x to the 4 plus 4x plus 1 dx. Now, I don't know what the antiderivative of that thing is. If you guys can find one, I'd be thrilled to see it. Yeah, go ahead. It's not open. So since we don't know what an antiderivative is, we can't do our typical thing, which is to find an antiderivative and then change the infinity to a b and then plug in and take our limit, right? Like that's the technique that we had from last time. So now all of a sudden we have one where that technique just fails right out of the gate. I don't know what an antiderivative of that is. And in fact, I hardly know what any antiderivatives are. There's so few that I can do that, like, if we had a way to get information about that integral, even if we can't find an antiderivative, well, that's a very powerful thing. So here we go. We're going to take this guy and we're going to boil it down to like its bare bone basic, most basic structure. So what that means, if x goes to infinity, there's some stuff in here that isn't all that important. For example, if x is enormous, then would you guys agree that adding 1 to this denominator has hardly any impact? Like if x is a billion, then a billion to the 4th plus 4x plus 1 is not that far different from saying it without the 1, yeah? Like relatively speaking. And in fact, if we can push the limits even more, would you guys also buy that the 4x is not all that important if x is a billion? Right, the billion to the 4th dominates. And so now we're starting to use this language of pre-calculus, you might remember, about like, hey, if x is huge, then it's really only the leading term that makes any difference. And so we're going to ignore everything except the leading term. So I'm going to come up with a brand new integral here, and that brand new integral is going to be just the leading terms on top and bottom. If the top had more stuff, I would ignore it. Just the leading terms. So this is a brand new integral. We're going to clean this thing up. What can I take outside? 4. And simplifying the x's gives me 1 over x squared. Yeah? So in my heart of hearts, if I believe that the highlighted stuff is pretty much irrelevant when x is large, then I have to think that the new integral and the original integral have the same convergence behavior. They either both converge or they both diverge. They both do the same thing because I ignored some stuff that was pretty much irrelevant. But this 1 over x squared is one of our things in our list on the previous page. So let's go find 1 over x squared. We've got this useful integrals for comparison list. you have two different ones that say 1 over x to the, what power is it? N or p? 1 over x to the p, but they have exactly opposite conclusions. So you've got to make sure you're reading the correct row of row 1 or 2. Which is the one that's relevant here? It's row 1 because we're going from 1 to infinity, right? It's the infinity row, not the 0 to a number row. So this guy right here has what value of p? 2. And 2 happens to be greater than 1. Which you wouldn't imagine you'd write such things in a calculus class, but that is a really important fact because it gives us the conclusion. 2 is the power in question, right? P is equal to 2, which is greater than 1. So by our, I'm going to abbreviate. No other mathematician is going to know what we mean when we say UIC, but for us, useful integrals for comparison, right? So by the UIC, what does this integral do? Converges. Okay. Yes, just like that. Yeah. Even for the what? Oh, no. So on the test, I will probably, yeah, actually, I don't know. So I'll be clear. On the test, it'll say, does it converge or diverge? And if it converges, find it. If it says find the number, then it's not this anymore. But there probably will also be a question that says just use the comparison test to decide if it converges or diverges. Don't worry about doing antiderivatives. Okay, so we're pretty much there. We know that the comparison test says that these two things, oh, sorry, I forgot an important thing here. How does this compare to that? We started with the original fraction. I ultimately made it look like 4 over x squared. The denominator of the first fraction, how does it compare? Oh, I'm going to change it to before we cleaned it up. Okay, how does the denominator compare? The first denominator is for sure bigger, right? We're going x is a positive number here. So 4x is positive plus 1 is positive. So the bottom of the first fraction is bigger. So when the bottom is bigger, what about the whole fraction? First one is smaller. And by that, if the denominator of the first one is bigger, then the whole first fraction is smaller. And this is our 4 times 1 over x squared. And so we have our integrand is definitely smaller than another integrand. And we know that this other integrand converged, right? And so by the comparison test, what about our integral? It also converges, right? Our integral is smaller than this finite thing. And that's our last sentence. So by the comparison test, we'll just abbreviate that CT. You're going to copy that whole original integral. It also converges. Chris. I need to see the phrase comparison test in there. Okay, so first again, our conclusion. We found that our integrand, our fraction, was smaller than this other one, but this other one converged by our useful integrals for comparison. And because our integral is smaller than a finite integral, our integral must also converge, and that's the comparison test. So just taking a big picture view at our first proof. This is the first proof we have written together. Perhaps this is the first proof you have ever written. I don't know. But part of what we're after here is just kind of this mathematical thinking and laying things out and writing proofs. And writing proofs is a very different skill than doing calculations. You guys have tons, years of experience doing calculations in math class. This is a little bit of an intro to proofs. It's a different kind of skill, still in the umbrella of mathematics. The whole thing is a proof. We didn't actually do any calculating, right? Like there's no solving for x, there's no antiderivatives that we did. The whole thing is just a logical sequence of steps that's supposed to convince the reader of some fact. And the nice thing about starting proof writing with stuff like this is that it's pretty formulaic. Like the proofs are generally this, you know, kind of like you can go anywhere at any time and use any tools available. But these have pretty much the same structure every single time. You change your complicated integrand into one that's simpler. You use your useful integrals for comparison to make the conclusion about the simpler one. You make sure that your integrand compares favorably to the simpler one. Remember we talked about how there's two good conclusions and then two things that you can't conclude anything for. You got to hope, cross your fingers, because you don't have a lot of control over that. You hope that the comparison works in the right direction, and then you just make your conclusion. Hey, comparison test says we win. They both behave the same. Okay, so now that we've got one under our belts, the second one will be easier. Let's try this guy. Okay, this one right here, again, I have no earthly idea how to find an antiderivative of that. I'm not just being modest, I'm being truthful. I don't know what to do with that. Let's drop the one. How about that, right? Okay, so we are going to drop the one and we're going to think about the integral from 2 to infinity of 8 over the cube root of x squared. What's that? Yeah, let's bring that 8 out. We want to make this integral as simple as possible and then hope that we know something about it. And then as Ben says, that radical we can change into a power. It's x to the 2/3. Hey, we can. 1 over x to the 2/3. That's another 1 over x to the p. Again, you've got two rows. Make sure you're in the correct row. This is one of the infinity ones. So which row is it, 1 or 2? It's row 1 again. But if this was a 0 to 1 integral, or 0 to some finite number, it's row 2. Okay, so how much is p in this case? P is 2/3, which is less than 1. So this integral, what does it do? Diverges by the useful integrals for comparison. Well, we need to figure out whether it's smaller or bigger. But we don't know. Let's see. Yeah, I mean, if the inequality goes the wrong direction, then we can't conclude anything. Let's see what happens here. We're going to try to compare the original to Ben's idea of just dropping the 1. First denominator, bigger or smaller than the second denominator? Smaller, because it has a -1 in it. So if the first denominator is smaller, then the entire first fraction is bigger. Is that the direction that's helpful for us? It is, because our integral is bigger than something which diverged. It's bigger than infinity. So our integral must also be infinity, must also diverge. So by the comparison test. And then again, copy the whole integral, the original one. 2 to infinity, 8 over cube root x squared minus 1 dx. What does this integral do? Diverges. So last words of wisdom here before we do the activity. It is really tempting to just get a tiny bit lazy and instead of writing this whole integral again, say the integral. The integral diverges. You're losing points if you say that. There's two integrals on the page, right? You cannot say the integral and have it reference only one thing and expect that the reader is going to know what you're talking about.
Could you
right?
say integral equals?
But if you call it I, right, we called the integrals I. So if you call that original guy I equals in the beginning, sure. I, yeah, that's totally fine, as long as you are referencing it specifically. But the integral, that is vague. Even worse, it, oh goodness. It's the reason I have no hairs. I pulled it out because people say it converges, or it diverges. What am I supposed to do with that? There's so many things on this page. What is it? So don't be lazy. Just recopy, or if you really wish, you can give it a name and then reference it. Yeah, that's okay. All right. There is a typo on page 27. Can we just fix that real quick? Page 27. Can you change in 5B? It says trig sub 5B. Change that to U sub on page 27. Everybody got that?
So the question is,